Hello. In a recent video we asked the question, does the Taylor series for a function converge to the function? In this video we're going to look at some of the techniques used in answering this question. So the question of convergence of a Taylor series to the function f that generates it is asking something of this nature. So does f of x equal the sum of its Taylor series? There's many equivalent reformulations. Because a series is defined to be the limit of its sequence of partial sums, we can recast this statement in this way, asking, does the limit as n goes to infinity, sum k equals 1 to n, k to the f of a divided by k factorial, x minus a to the kth, does that equal f of x? In an earlier video, we introduced notation. This partial sum we see here, remember, was called the nth Taylor polynomial, and we denoted that by p sub n. So there is another equivalent statement to the one asking about convergence of a Taylor series to the function that generates it. And a fourth way to do this, we could actually, instead of looking at the limit statement in line 3, realize that if Pn is approaching f, then f minus Pn should be 0. So we can also ask, is this limit, fx minus Pn of x, as n goes to infinity, equal to 0? And of course, if something goes to 0, then it gets small. And so we're actually going to address this question in the form of this last line, taking a look at the difference between f and a Taylor polynomial, and ask, does that get small when n gets large? So to investigate some of the techniques used in answering these questions, we're going to take a look at this example. We're going to let a function f of x be the arctangent of x, or the inverse tangent of x, and answer the following three questions. We'll find P3, the Taylor polynomial of degree 3, centered at 0. We'll then find a numerical upper bound for the error if we use P3 to approximate the arctangent. This is where we look at the difference between arctangent of x and P3. And then finally, we'll say, suppose you want the approximation to be within 10 to the minus 6th of the arctangent. Is there an interval on which that happens? We've denoted that interval as minus c to c. So for part A, we're going to take a look at two different ways to find a Taylor polynomial. So the Taylor polynomial P3x at 0 was defined in earlier chapters and videos in this way. It is just the sum you see here. The coefficients of the x minus 0 to powers terms are just various derivatives of f at the point of expansion, the 0 point, and then divided by various factorials. So we're going to calculate these coefficients by finding the derivatives of the function f of x, the arctangent function, and evaluating these derivatives at 0. So this is something from Calc 1. So to go through the steps kind of quickly here, the 0th derivative of a function is the function itself. And so we start off with just the function evaluated at 0, which is the arctangent of 0, or 0, and that is the constant or lead term in the series. Remember, the derivative of the arctangent of x, or inverse sine, is 1 over 1 plus x squared. When x equals 0, this becomes 1, so f prime at 0 is 1. Using the quotient rule or chain rule, we can compute the second derivative. You should do that, separate piece of paper. Plug in 0. We see the second derivative at 0 turns out to be 0. And finally, using the quotient rule and chain rule together, we get the third derivative looking like this. Again, try this on your own. Make sure you can do it, because you'll have to remember how to do these derivatives when you generate your own Taylor polynomials. We plug in 0 for x. We find the third derivative at 0 turns out to be minus 2. So the Taylor polynomial, recall, looks like this. And so in that template, we just have to put in the various values of the derivatives we've calculated. So the fact that f of 0 is 0 gives us this lead term here. F prime of 0 was 1. That's right up there and here. The third derivative was minus 2, which you see here. And then those are multiplied by various powers of x minus 0. And of course, we've already collapsed this x minus 0 to x right here. We'll do the same thing in the other terms to come up with just x minus x cubed over 3. So a pretty simple Taylor polynomial. Now we can also get a Taylor polynomial from a Taylor series. The Taylor series centered at 0, remember that's called the Maclaurin series, for the inverse tangent function can be found by looking on page 620. There's a table of frequently used power, actually Maclaurin series there for various functions. You should know these by the time the first exam rolls around. Now, the arctangent or inverse tangent function is given in this table, and we're told it has the following Taylor series. And you can see in this Taylor series, the Taylor polynomial P3 is sitting right here. And so if we were just to cross out all the higher order terms, that is, throw away all terms of degree greater than 3, we would have that Taylor polynomial. So this works for any Taylor polynomial. If you have the Taylor series about the point of expansion A, you can always get the series by doing this kind of truncation. Now, often you find one Taylor polynomial might equal another. In this case, P3 and P4 are the same, because if I were to ask for P sub 4, then I would throw away all the terms of degree greater than 4. It would be the same terms, and we'd be left with then just x minus x cubed over 3. The fact that there is no x to the fourth term means that P3 and P4 are the same. So it often happens that two consecutive Taylor polynomials are identical because of a 0 coefficient in the Taylor expansion. Okay, so let's take a look at the error. In determining when a power series converges to a function f, we're interested in looking at the limit of the Taylor polynomials, asking, do those Taylor polynomials get close to the function? Is the difference small? So when we talk about difference, we use this notation, capital R. R actually often stands for remainder, but it also is often thought of as the error. So if you're interested in an approximate function like the arctangent by P3, and you want to know how good that approximation is, you're asking how big is the difference between the polynomial and the function. So we're going to be working with this R3 and estimating it, trying to find out how big it actually could get on the interval from -1/2 to 1/2. So this is a part of some general notation we'll review right here. If we have an nth degree Taylor polynomial centered at A for a function g, then the error in approximating g by Pn of x in the approximation is this. So here is how we might denote Gn is approximated by Pn, which again is this nth degree Taylor polynomial. And when we want to discuss such an approximation, we'll normally look at the remainder or error Rn, which is how much g of x differs from Pn of x minus a. So Rn is defined to be the difference between the function gx that generated the series and its nth Taylor polynomial. Now, when we go to ask how big this difference is, we'll normally look at the absolute values of the remainder. We're not going to be so concerned whether that remainder is negative or positive, but rather how big it is in absolute value. So we'll usually be looking at the absolute value of Rn, or absolute value of g of x minus Pn. And we'll see in our textbook, as we saw, that there is a nice, well, not too nice, but there is a way of estimating or getting a bound on how big this difference is. It is this result. So the idea is that the difference gn minus pn is no bigger than mn plus 1 over n plus 1 factorial over x minus a to the n plus 1. Normally when you apply this formula, you will know n. It'll be just a value like 5, 6, 7. So you will know n plus 1. Just add 1 to whatever n is the index of the polynomial down here. And the mn plus 1, this is the new part here, it is any number greater than or equal to the maximum value of the n plus first derivative of the function, which should be g, on the interval a to x or x to a. We write them both because if x is greater than a, we would use this interval. If x is less than a, we'd write it this way. So mn plus 1 is the tricky thing to get a hold of here. We have to actually generally compute that n plus first derivative of the function. In other words, one derivative beyond the last one used in the Taylor polynomial, and then find a number bigger than the absolute value of that derivative. So let's go back to our problem of approximating arctangent of x by its third degree Taylor polynomial centered at 0 on the interval minus 1/2 to 1/2. So we're going to use the error bound just discussed. So if we're looking at how much f of x differs from its third Taylor polynomial, that is R3, the third remainder. Now, according to the formula we saw on the previous slide, because we're involved with P3, we have m3 plus 1 over 3 plus 1 factorial x minus 0 to the 3 plus 1 power, or m sub 4 over 24 absolute value of x to the fourth. And again, m4 is any number greater than the absolute value of the fourth derivative of the function involved, in this case the arctangent, on whatever interval we're working on. Now, to find a candidate for m4, we're going to have to work with the fourth derivative. Now, because x is in the interval from minus 1/2 to 1/2, we're going to determine m4 with regard to this interval. So m4 is going to be the largest, or a value bigger than the maximum of this fourth derivative on the interval. So we calculated the third derivative back when we computed P3. And if we differentiate that third derivative, again, product and quotient rule, we get we get the following form. Okay. Now, question is, how big is this? In fact, if we want to know if we take its absolute value, how big is that? What is a number bigger than that absolute value on the interval from minus 1/2 to 1/2? Now, we saw ways to find maxims of functions back in Calc 1. We could actually apply those in this case on the interval minus 1/2 to 1/2. But because we aren't concerned with the exact maximum, but just something bigger, we can actually often do this by just looking at a graph. So once again, our goal is to determine m4, which is any number bigger than or equal to this absolute value of the fourth derivative on the interval minus 1/2 to 1/2. One quick way to do that is simply to graph this function, this y equals absolute value of the fourth derivative. And here's what the graph looks like. So this quantity is small at 0. It gets bigger, then it seems to come back down. But we can see from the graph that from minus 1/2 to 1/2, this graph seems to stay below the level 5, and so 5 would be an okay candidate for m4. Notice the 5 is a little bit, it's actually bigger than this function all the way across. We could have gotten by with something a little less, maybe 4.9, but generally I like to, if I don't have to go too much bigger for m4, or m sub n plus 1, make it a nice number. So I'd rather work with 5 than 4.9. So I'm going to declare from the graph, I see this is no bigger than 5, and I'm going to use that for my m4, for my maximum of the derivative. So there's a discussion of how we did that, working on the interval from 0 to 1/2. And so let's go back to R3 then. So R3, again, the difference between the function we're working with, the arctangent, and its third degree Taylor polynomial at 0 in this case. If we replace the mn plus 1 which in this case is m4 with 5, then we get that result. So the 5 comes from up here. Here is the 4 factorial in the bottom that we worked with. And here is the absolute value of x minus a. A is 0 to the power 4. Okay. And when we do all that arithmetic, we come up with 0.013. Should add here too, because we're on the interval from 0 to 1/2, we know that x can't be any bigger than 1/2. So again, to get a numerical upper bound, I replace x by the largest it could be, and that's 1/2. And so whatever this difference is, it's going to be no bigger than 0.013 for any x in the interval minus 1/2 to 1/2. Again, we find the m5 number, or the m4 number, which is equal to 5 in this case. To take care of the mn, we make x as large as it can be, because to get a numerical value, I have to get rid of that x. We always want to keep making this thing bigger as we move to the right here, so that we are getting something truly bigger than this difference. Now, we can investigate this error in another way too. We're going to look at this error graphically just to see how our estimate compares with a true error. Often trying to graph an error like this is difficult, especially if you're looking at P3 or Pn for a large n, or f is complicated. But in this case, it's not too hard to enter this and graph it on the calculator or computer. And there's what the error actually looks like. So we can see here as we go from minus 1/2 to 1/2, here's how big fx minus p3 is. Notice it really is pretty small. We're at 0.005 up here, 5/1000ths. And so it looks like really this is less than 0.006. And remember, the error we got was 0.013. So these remainder estimates will always give you something bigger than the actual error, but often this actual error is almost impossible to get, so we have to be satisfied with an estimate like 0.013. Notice too, as we'll discuss in the next slide, as we get the error, as you get close to the 0 point, the expansion point 0, the error gets smaller and smaller. It's extremely small down there. We can't even see how far off the axis it is with this resolution. Okay, sometimes we want to do an approximation and we want to guarantee that our approximation is not off by more than some small tolerance. So in this case, we're going to find an interval C on which the error is less than 10 to the minus 6th. So we can see again back from this slide, with this picture of the true error, that that's going to happen on some probably pretty small interval here close to 0, something inside the interval from minus 1/2 to 1/2. So the minus C to C might go something like this. Okay. So we're going to actually use that realize we are within the interval minus 1/2 to 1/2 and see what happens here. Okay, so because we're in the interval minus 1/2 to 1/2, so that the C is going to be somewhere beside there as we just saw, we can still use our M4 equal 5. So if we go to a smaller interval for our error term, whatever bound we had for that fourth derivative on minus 1/2, 1/2 will still hold, even though again it might be much larger than we need. But just for convenience and ease, we'll go ahead and keep M4 equal 5 in our calculation. So we want to look at, again, R3, the difference between the function arctangent and its third Taylor polynomial. We saw in the previous slide this was no bigger than 5/24 epsilon of x minus epsilon of x to the fourth power. And now, in this application, we know that the x is going to be no bigger than this number c we want. And so whatever the error is on whatever interval we're working on, it'll be no bigger than 5/24 c to the fourth. And we want this to be less than 10 to the minus 6th. So we're going to pick a c so that happens. So this is an easy inequality to solve. 5/24 that's the c to the fourth less than 10 to the minus 6. We can isolate the c to the fourth by multiplying both sides by 24/5, and then take the fourth root, and we find we get this interval. So this is our c value, the interval on which the P3 is within 1/1,000,000th of arctangent is pretty small, only going from about minus 0.0468 to plus 0.468. So we'll go ahead and take c equal to 0.046. That's a little smaller, so it gets us even more inside. And again, it should be clear that any c less than this number would have worked also. So we can say if we use P3 to approximate the arctangent on this interval, so any x's come from there, then the error in that approximation does not exceed 1/1,000,000th. Now earlier we saw that P4 equals P3. You might want to think about how would this result have differed if we'd had P4 instead of P3. If we instead worked with P4, then of course we'd have to consider m sub 5, which is the max of the absolute value, or something bigger than the max value of the fifth derivative. And the n would be 4, the n plus 1 would be 5. So does that change the calculations? How would you resolve this question? So you might go back and rework this part C exercise using P sub 4 rather than P sub 3. So the takeaways are this. So the first thing we had to do in part A was find a Taylor polynomial. And we saw two ways to do that. One way, of course, is just to get out the Taylor polynomial formula, which is this, expresses the polynomial in terms of various derivatives of the function f at the point A. If you calculate all those derivatives and plug them in where they show up here, you will have the nth Taylor polynomial. You have to compute n derivatives, so if n is big, this could be a lot of work. A second method that is quicker if you have the Taylor series for f about the point A is just this, is you can then get the Taylor polynomial by just throwing away all the powers of x minus a that are bigger than n. So feel free to use either way to do this. And this is one reason why those given Maclaurin series on page 620 can be useful to know, because the more Taylor series you can write down, the more Taylor polynomials you can compute quickly. The second takeaway was the business of the error. So if we want to know how much a Taylor polynomial differs from a function f, and of course those are important questions if you're asking, are the Taylor polynomials actually approaching f? We investigate that question by looking at r sub n, which is the difference between the function f and whatever Taylor polynomial we have in mind. We usually look at the absolute values of the errors because we're concerned with how big it is in magnitude. And we saw that this error is no bigger than this quantity mn plus 1 over n plus 1 factorial exponent a to the n plus 1. Again, you'll usually know n in this case as some integer, so n plus 1 will be known, and you can make the calculations. The mn plus 1 is the harder part. It is any number greater than or equal to the maximum of the n plus first derivative on the interval in question. We usually say a to x or x to a, but if you're told to work on some interval like minus 1/2 to 1/2, then you can take your mn plus 1 to be a number bigger than that absolute value of the n plus first derivative on that given interval. So there's a lot to these problems, a lot of little nuances, definitely something you want to practice before you encounter these in an exam situation. So thanks for listening. Bye.